last time we built the ALU. It can add, subtract, and perform logic operations such as AND or XOR. But it has a problem. The moment the inputs change, the old result vanishes. It has no memory. To build a real computer, we need circuits that remember. What if we could trap a bit of information and hold on to it? Here's the trick: feedback. What if we connect the gate's output back to its own input? This creates a loop. And it turns out that loops can hold state. Meet the SR latch. The S is for set and R is for reset. It's just two NAND gates which are cross-coupled. This means each gate's output feeds into the other gate's input. Two feedback loops working together. Let's see it remember. First, let's pulse S low, which means setting S to 0 to set the latch. Q becomes 1. Now let's release S back to high, which is setting S to 1. Q stays at 1. To reset, we pulse R low, which means setting R to 0. Q becomes 0. It remembers the last command. We just built a 1-bit memory. It remembers which button we pressed last. But there's a problem. It changes whenever S or R changes. We need more control. We need to capture data only when we want to. Enter the clock signal. Think of it as a heartbeat for the circuit. It ticks at regular intervals, and it controls when data is captured. Let's build on what we learned. We start with our SR latch and add two steering gates controlled by the clock. D connects to one gate and not D connects to the other. The clock controls when data passes through. When the clock is high, D flows through. When low, the output holds. This is a D latch. Put two of them in series and you get a D flip-flop. The second latch gets an inverted clock. So they take turns, one captures, the other holds. When clock is high, the first latch captures D, but the second is locked. When clock goes low, the first locks and the second captures from the first. The result? Data only reaches Q on the rising edge. The D flip-flop captures its input only when the clock ticks. In this setup, D is the data and Q is the output. On the clock's rising edge, Q captures whatever D is. At all other times, Q just holds its value. Let's see it in action. D is 1, clock ticks, Q becomes 1. Now D changes to 0. But Q stays 1, it's holding the old value. Clock ticks again, now Q captures the new 0. We have synchronized memory. Data is captured precisely when we want it. There is a small issue. One flip-flop stores 1 bit, but we work with 4-bit, 8-bit, 32-bit numbers. So we line up multiple flip-flops, all sharing the same clock. And now we have a 4-bit register. Let's see a 4-bit register in action. On each tick, they capture a 4-bit value together. Let's store the number 5. That's 0101 in binary. Clock ticks, the register captures it. Registers are the CPU's working memory. Fast, close to the action. So while registers are fast, they are also limited. What if we need lots of memory? Enter RAM, or random access memory. RAM allows us to access memory at any location and any time. Think of it as a grid of memory cells. Each cell is a full clock. Address bits select which cell to read or write. With 2 address bits, we can select 4 locations. A decoder takes the address and enables exactly 1 row. Address 10 lights up the 3rd location. Imagine millions and billions of these cells. That's the RAM in your computer. Now let's step back and see what we've built. From feedback loops, we build memory. The SR latch, the D flip-flop, registers, RAM. Now our circuits can compute and remember. We now have an ALU and we have memory, but something's missing. We need something to orchestrate them. Something to fetch instructions, decode them, execute them. Next time we build the CPU.